The paper is titled Photo-Inspired Diffusion Operators. So first, let's understand what's going on. So in this, we would have a model which would be working on an image embedding space, which is on a lower dimension. And this image space is known as the clip image embedding space. The goal of this paper is to train a model in order to understand and apply certain operations, such as the union operation or the texture operation, in which you apply a certain texture to an image. Or you can also have one sec. The instruct operator, which consists of several images combined together, and the scene operation, in which you can add a scene to an object to get an output. So these operations, just like in math operations, are pretty fundamental to performing several types of manipulations on an image. And after having trained the model in order to understand these operations, we'll apply an image diffusion model in the embedding space of the image. So now let's first try and understand what clip exactly means. Clip refers to contrastive language image pertaining, which was developed by OpenAI. Um, it is a model which uses both images and text in the embedding space, and it maps both of them to a fixed vector. It uses a contrastive learning approach to train the model. In this, we differentiate between correct and incorrect pairings of images and text. It consists of both an encoder. It consists of two encoders, one for processing images and another for processing text. It transforms images and text into a shared embedding space. This is what Clips does. So after having understood what Clips does, let's understand what's exactly going on. So just like basic arithmetic operations in the field of mathematics, in the field of visual content generation, text is pretty much the most basic form. Text plays the roles of operations just like in math. However, it has several disadvantages. For example, you can't get precise control over the generated content just by using text. This often requires prompt engineering, which involves um, carefully crafting and refining the input text given to the model in order to guide the output. For example, if you want an image of, let's say, a dog playing on a sunny beach, just by typing out this image may not give you what you want. And therefore, you'll have to continuously keep on editing the prompt that you have entered in order to get the prompt that you want. So in order to overcome the issues of just having texts followed by images, the paper draws inspiration from constructive solid geometry, which is this paper, in which you can see a 3D image being constructed by a simpler 2D image. For example, this cylinder being swept by an entire rectangle, or a cube that is being swept by a square. Mm. So just as you saw in the constructive solid geometry paper, the authors want to apply simple operations in order to generate images. These operators would again work on the clip image embedding space. Now, clip has been discussed about in this paper. Mm, yeah, I can't find the paper for some reason. So, so, uh, so in the paper in which Clips was discussed, uh, they realized that in Clips, the embedding space captures several images, captures the meaning and relationships between images. And within this embedding space, you can perform several mathematical operations such as addition or subtraction on the image vectors, such as these. And this would result in new vectors, which also have meaningful content. For example, you could add a code to this in order to get this, or you could add a cat and a hat in order to get a cat wearing a cat wearing a hat. However, this also has issues because you can't directly work with vector spaces. For example, the user cannot directly interact with these vector spaces. Uh, doesn't refer to adding the two vectors together because we need to combine them in order to get something meaningful. So, uh, not sure. Right. So, as we were talking about, there are some issues because the user can't just interact with vector spaces. Therefore, to address this issue, the authors propose POPS, which is a framework in which you design just specific operators. These operators are functions that can be applied within the clip embedding space to perform desired manipulations more precisely. So, so each operation in this framework is designed to perform a specific operation. For example, one operation might add a particular object to an image, while another might just change the scene settings, as can be seen in this example. For example, we are adding texture to this object, or we are adding a background to this object, or we're considering the union of these two in order to get this. So these are just binary operations. There are also operations involving several images, such as these, where you'll have several images and you'll get an output. So these are several operations in the framework. So before we get into this, before we get into understanding the method that is used in this paper, we need to understand what a diffusion prior model is. So a diffusion prior model was introduced by Ramesh in 2022, and it mainly involves mapping input text embeddings to corresponding image embeddings within the CLIP embedding space. Um, so in a diffusion prior model, the primary goal is to map the textual descriptions, which is in the form of an input, to the image embeddings. These image embeddings then would help us form a model for image generation. So this has been used in several places, as can be seen from these papers. They were used in uh, they were used in creative image generation, in which uh, we just create images from the text. Then we'd also have text to video generation, in which we apply the concept in order to generate videos from the textual descriptions. Then we also have 3D generation, in which we explore the application of the diffusion prior models in order to generate 3D content. So this was about diffusion prior models. So now let's talk about the method that is actually being used in this paper. So we first have a diffusion prior in order to map the text embedding to an image embedding. After that, we feed the text embedding into a diffusion prior model to map a given text embedding into a corresponding image embedding. So this involves two steps. First, we need to train the diffusion prior model, and we'd also have to train the DDPM. In order to train the diffusion prior model, uh, we want to model it for a specific task. And for example, let's say applying texture to an image. So in this case, um, we need to pass in several inputs. So we first pass in uh, at each timestamp, we'd first pass in the embedding of two images, the object, which is this one, and the texture. Then we'd also pass in an encoding of the current timestamp, which is this, and we'd pass in a noised image embedding as well. Uh, so there's a denoised representation of the final image embedding. So the output that we would get from this would be a denoised image embedding that matches the target embedding, such as this one. So after we have trained the diffusion prior model, we'd have to pair it with a pre-trained diffusion model. So we have both. We have a diffusion prior model, and we'd also have a denoising diffusion probabilistic model, which is the DDPM. So in order to pair it with a pre-trained, in order to pair the diffusion prior model with the pre-trained diffusion model, so after this is, so for example, in this case, the diffusion prior model is used to predict the denoised image embedding E uh, when from a noised image embedding ET at timestamp T and text prompt Y. And the DDPM is used to produce in order to remove the noise that is added at the timestamp T, given a condition vector C. This condition vector is currently an image embedding. Um, yeah, it's done for each operator, if I'm not wrong. For each operator. Yeah. So for example, for texture, it'll be different because you'll have two images for texture, and then for union, you'll also have two images, and then for something like an instruct operator, which will have several images, it'll be different. So yeah. So the sorry, the the diffusion probabilistic model acts as a renderer. So the embeddings produced by the diffusion prior model are often abstract and high dimensional vectors. So we want the renderer in order to translate these abstract vectors into a detailed visual representation. Now, as I said, uh, we will talk about the various operations that can be performed. So most of these operators share the same architecture. However, they differ in terms of the input conditions and corresponding training objectives. I mean, it is trained for each operation, right? So for example, we're passing the image embedding just for this operation. No, it's trained for an operation, if I'm not wrong. Yeah, I think so. Yeah. So let's talk about the architecture and the training. We'd have a pair of input conditions and a corresponding target image. So after we have we'd have the pair of the images IAIB, and we'd have a target image I target. After we have the pair of images, we would operate in the image embedding space. So in this, the images are encoded into embeddings using a clip image encoder. So this would generate tokens EA, EB, and E target. So the original prior model received 77 input tokens, which would originally correspond to the clip text encoders. How we can change the meaning of the inputs in order to just have the two embeddings EA, EB, and we can fill the rest of the entries with just with just the value 0. So in this, the diffusion prior model is trained by just adding noise to the target embedding and learning to denoise it like this. We add a corresponding noise, which will result in a noisy image embedding, E target T. And we train our prior model using the standard denoising objective, which is just this, which is this is the target. And these are the two tokens EAEB, and this is the timestamp T. This is just the L2 norm. So after this, let's talk about data generation. For example, in several specific image-to-image tasks, it was often common to just have task-specific modules to the architecture. For example, there was a depth estimation model in which there's a model dedicated to just estimating the depth in an image. and there was a background extraction model, which was just designed to isolate the object of interest from the background. However, in the case of pOps, there's a unified architecture for all binary operations. So instead of adding just task-specific modules, the pOps framework uses a unified architecture for all binary operators. The model learns to manipulate the image embeddings to perform the desired task without needing to separate uh, and have dedicated modules. So, um, wait, which one? This one? Mm-hmm. Right. Right. So the way I understood was it considers the union and then it just splits it by the objects inside it. But yeah, where's the diffusion prior in this? Yeah. See the. Mm-hmm. Yeah, I mean, I see your point. I can't. Hmm. Okay. Let's talk about some of the operations that are performed in this. We would have the texturing operation. In this, we would have the image embedding of the object and the texture that's to be added, which is the e texture, which would represent the desired texture. So our goal in this is to create a target embedding that combines the object embedding with the texture embedding in order to get the target embedding. Sure. Mhm. Sure, sure, sure. Yeah, sure. Oh, we're trying to figure out something about the union operation. वो बोल रहे यूनियन में डिफ्यूजन जो है काफी यूज हो रहा है तो पूछा है ग्रुप Nice. So we had other operations as well, such as texturing, scene, and union. For example, in texturing, we intend to add a texture to a particular object. So we have two embeddings, the texture and the object embedding. And we do this by first getting an object using SDXL Turbo. SDXL Turbo is it's a model in the Stable Diffusion series that is designed for just faster image generation. So so the object that the image that we got from this is it has the image embedding of e object, and we use this while training. So we get a set of attributes that are associated with this, and wait. So yeah. So we get the set of attributes that are associated with the texture. Then a subset of these attributes are selected and composed to get a descriptive sentence. For example, in this case, we have a set, and we select some of them. So we and there's the object right now, and there's the target. So um, after that, after we are done with selecting a subset of these, we'd have an image which is generated using the stable diffusion model, which considers the depth of the generated object image and the composed text prompt. This image represents the object with the new texture. So this was the texturing operation. Now, in the scene operation, we have the input embeddings, which consist of yeah. Yeah, I mean, there could be some issues with the paper. I actually don't know. So, uh, so we'll just talk about the scene operation and then we're mainly done. So in the scene operation, we'd have oops. In the scene operation, we'd have two input embeddings. We'd have the object and the back. The object represents the object of interest, and the back represents the target scene background. So again, in this case, we use SDXL Turbo in order to generate an image of our object, and the resulting image corresponds to the target embedding. So this is our target right now, and our goal. And we remove the background using BRIA 2024, and this would help us isolate our object from the generated image. The isolated object is then placed on a white background or within a newly generated background. This image is encoded into the object embedding. After this, in order to have a background generation, we use a stable diffusion model to produce an image containing only the original background. This background is encoded into the background embedding. So so we produce an image containing only the original background, and we encode this to the background embedding. And but during the data generation phase, we decompose the target into separate representations of its object and background. And through this process, pOps can learn how to effectively compose the two elements back together. This was similarly done in the union operation, in which we again had two image embeddings representing two objects, EA and EB, and we want to combine both of them together. So we construct a data set of images containing pairs of objects by randomly selecting two object classes and generating an image which contains both objects. And this is defined as e-target. And we split them in order to get the interested the interested parts of the objects, which are EA and EB. And this gives us the union operation. Finally, we would have multi-image composition, which is not just binary, but combines several input embeddings simultaneously. And this will involve multiple elements. For example, in this case, we can combine several pieces of clothing together to represent a person wearing clothes. And the way this is done is we extend the input sequence in order to accommodate for the set of clothes. And we use the fixed index for each of the item and train the model just like we trained the binary model. Um, yeah. And we finally talk about the instruct operator. In this case, we generate an embedding that modifies an object's appearance based on a descriptive adjective. For example, if we have, let's say this as the input, and the text, the adjective is cracked, we would have it is cracked. Or when we have it's burning, we'd have that it's burning. Or if you have this as the input and we say enormous, this would make it enormous. Similarly, if this is the input and we say spiky, it would make it spiky. Similarly, for shiny, it'll just make it shiny. So in this case, we'd have the object embedding and the instruction, which is the adjective embedding, as the inputs. And in order to train it, we would feed both of them into a transformer, which uses the clip space embedding. And we introduce a loss in this case. And this evaluates the similarity between the generated image and the text, which was the original objective. And this is our new loss function now. So this denotes the generated embedding. And this is just a factor for the additional loss term. This was the prior loss. And these were all the operations. Um, the results, as you can see here, pOps does pretty well compared to most of its predecessors. And yeah. Oh, it does. See this thing? I mean, they wanted to add it to the loss, right? Because we don't have it incorporated in this. Because you want to find the similarity between the text and the generated embedding, right? Uh, do they change the values of lambda? Okay, I don't think they talk about lambda anymore. Oh, wait. Wait, I'm seeing. It was the instruct operator, right? Wait, they don't. Yeah, it shouldn't change it that much because it's just the similarity between the final thing and the text. Yeah. Yeah. Yeah, I don't know what to say about that. But yeah, that's it for the talk, and I don't have anything else to share. So yeah. Oh,